couple of minutes. Okay, so I think that we can start. Welcome everybody. This is my great pleasure to introduce MIAI, who is going to do the fourth Deeptails seminar, and the title is Towards Interpretable Computer Vision and Thorough Evaluation of Explanation. Usually, from what I understand, Deeptails seminar are presented by a researcher and a PhD student, but we thought that we could make an exception here because of the contribution that MIAI has been doing to the field of interpretable AI. So she's currently finalizing her PhD on explainable and interpretable computer vision, and she's, as you can see, affiliated with the University of Twente in the Netherlands and the Institute of AI in Medicine in Essen, Germany. She's going to talk about two things. The first one is how to evaluate explanations. And the second one is how to build a more interpretable by design systems, which is also a subject that we are trying to work on in the responsible and ethical AI chair here in MIAI. So the floor is yours. Just an announcement. Since the talk will be divided in two parts, you can ask your question in the chat, but also we will have maybe a short session of question and answers at the middle of the talk, and then we can go to we will go to the next part. Okay, so the floor is yours.
We cannot hear you.
Yeah,
your mic
okay.
is.
Yeah. Oh, you can't unmute yourself. Oh, can I unmute you? Wait, can I? Snezhana,
yes, can you now hear me?
Okay, yeah.
Yeah, okay.
That's fine. Great.
I don't know what happened, but somehow my Zoom wasn't visible.
So, yeah.
Okay, yes.
We're seeing the slide.
Yeah, now it should work. All right.
Okay.
Yes, so indeed, I'm going to talk about explainable AI, and then the next part will be about if you have images and you want to give them a label, how can you make models that are then also by themselves already explainable? So indeed, I started my PhD end of 2018, and I'm now already at the end of my PhD. I'm doing it at the University of Twente in the Netherlands, and also at the University of Duisburg-Essen in Germany. And before that, I did a master in also basically already specialized in data science, and in my recent interests are now about the evaluation of explainable AI and how to incorporate explainability already in the models rather than only trying to explain them after training the models. So the first part of this talk will be about the evaluation of XAI, and then if people have questions, we can already answer a few of them, and then I will move to the second part about models which are already explainable by design. So, well, I think there are many stories already in the media showing issues that are currently happening when we have AI, usually because users don't have insight into what the model has really learned. And that is, of course, why explainable AI is so important. And usually one could say that you can choose between either models which are by themselves already explainable or models which are not. And if you then look at explainability, you can either say, well, these are already explainable by design, so nothing has to be changed really. But usually, of course, the accuracy of simple trees is low. Or you go to different models, which usually have a good performance, but then you don't have explainability. But what you could do is then somehow look back by applying so-called post-hoc explanation methods to get insight into what has the model actually learned. And well, you could say, well, a neural network is actually also to some extent understandable to humans because, well, the weights are all there. So you could, as a user, simply look at the weight. So it's not that something is really hidden. It's just that currently the number of weights is so big that it's for a user not really explainable anymore. So what we should do is to somehow move from too many weights to something which is actually understandable to humans. So the definition that I then use for an explanation is that to a user you are presenting the reasoning, functioning, or behavior of a machine learning model in human understandable terms. And over 1 billion weights is then of course not a human understandable term anymore. So the challenge is to create explanations which explain part of the model in human understandable terms. And this then, of course, depends on the user. So the type of method that you want to use depends on what is the knowledge of the user. So you have people which are actually building and developing the models themselves. And for those, you can, of course, use a different type of explanation than someone who is just using the model. So the person knows something about machine learning, but not all the details. And of course, you again need a different level of explanation if you are presenting the explanation to a domain expert, which probably knows a lot about the data, but not necessarily about the model. And besides looking at the user, it's also very important to look at the goal of your explanation. And basically, you could identify 4 different needs for explainable AI. And of course, the first one is there is a model which is giving a certain output, and you want to know, okay, what is the reasoning of the model? Why is the model giving this certain output? This is actually now getting even more interesting because there was this law introduced in 2018, which actually also says that if there is if a model is used to make a decision about a so-called data subject, so a person, then this person has the right to know about the meaningful information about the logic involved. So with AI, there is actually already needed to give a certain justification of the outcome. The second one is actually to also check whether the reasoning that the model has learned is actually a bit similar as what you as a user expect. So is the model right for the reasons which you want it to use? So for example, we did some work with a data set about skin lesions. And basically the goal was then to train a model to find out whether there was cancer in an image or not. It turned out, however, out that part of the data set has these kind of read stickers in there. And these colored patches were only present in half of the images where there was no cancer. And all the other ones did not have those stickers. So when we just trained the standard model, we quickly got a good accuracy. But then if we analyze this further, we, for example, found that, well, this data set was biased and that the model had actually used this bias. So what we could do is that we, for example, could insert these colored stickers into images which actually did have cancer, or that we in-painted images which had stickers, and then we made sure that they were not visible anymore. And what we saw, for example, is then the misclassification actually increased. So in this case, for example, when we inserted those patches, then all of a sudden the model says that, well, this image wasn't containing any cancer anymore, which is, of course, quite a high risk if you would use this model actually in a hospital. So this shows that explainable AI is really needed, because only looking at the accuracy of a model isn't really enough to ensure that the model is doing what you actually think the model is doing. And actually this control is also then required for the next step, namely that you can then make sure that you can maybe make the model smarter. So you can change these biases, for example. So only if you have insight about what the model has done, only then you can, of course, make sure that the model can be developed further. And the last thing is that knowledge discovery is also a really great, useful for explainable AI. So there are already quite some examples available, like playing certain games or identifying certain types of cancer, where actually the accuracy of a machine learning model is higher than what a human doctor can achieve. So what you want is that you actually want to know, okay, what has the model learned? It could be that it is simply a certain bias, as we showed with the skin cancer. It could also be that there are actually knowledge in the data which we as humans didn't know that was available, which might actually be very useful for the task. So by extracting this information from the model, we might actually learn new insights, and therefore for the scientific insights, this can also be very useful. So when you then know, okay, this is the type of user I have in mind, this is the goal of the explanation, then you can decide, okay, what is then the type of explanation that that you think is most suitable for your use case. And there are actually quite some different types of explanations and explainable AI methods. So I've basically made this list of different types of explanations which are there, which of course depends on what you think is what your use case is on the user, but also on the type of input data. So you have feature importance, you can have a heat map, which is more for images, for example. But so besides the type of explanation, you can actually identify more. So what is the type of input data? What is the type of model you are explaining? What is the type of method that you are going to use to explain? So do you want to do it post-hoc, so after training a model, or maybe already build it into the model itself? What is the task that you have for your use case? And all of this together can then define basically what the best explanation method is to use. So this paper, what we did is actually that we try to find a lot of papers on explainable AI to then check, okay, how are they actually then measuring how good their method is? So how can we evaluate explainable AI? But to do that, we of course first had to see, okay, what type of XAI methods are actually there. So what we did is that we initially searched for papers which had something about interpretable ML of explainable AI in the title. And then we collected papers from these venues, so the conferences from 2014 to 1.5 years back. And then we collected all of them which actually were indeed then introducing or using a method on explainable AI. Well, you can already see that since like 2017, 2018, the attention for explainable AI was actually really increasing. And eventually we ended up with over 300 papers which were actually using or presenting a new method on explainable AI. So we actually then had the scheme of how to classify XAI methods, and we have actually added this on a site. So you can then basically search for the explanation methods which are fitting your use case. So if you say, okay, I want for input data, I want images and text, for example, and then you can see, okay, now I want to see all the methods which are either made for image and text, or for one of them, based on one certain one certain type of. And in that way, you can basically find all the papers which you think are fitted for your use case. So we have now more than 300 in there. So I think this is a very useful starting point in case you want to search for explainable AI methods. And then we, of course, classified all of them. And then we found, for example, that, well, images and text is actually the input data which is used most. And, for example, feature importance and heat maps are actually also one of the most used types of explanations. And, of course, the deep neural networks are the models which are actually used most to explain. So then, well, based on this, you can maybe then already get a set of explanation methods which are suited for your goal, do have the type of data and that you need and the type of explanation you need, and are suitable for your intended user. But then still, the question is, okay, what is then the best XCI method? Because there are probably more. So basically, how do we measure the quality of an explanation or of an XCI method? So for that, we actually investigated the evaluation of explanations. And we can basically divide that into two questions. So the first is, okay, what actually makes a good explanation? So what do papers say of what is a good explanation, what is a bad explanation? So for that, we read a lot of papers to eventually come up with a list that basically discusses what a good explanation then is. And then the second one is that we then analyze, okay, and how can we evaluate that then for explainable AI? So we did this structured literature review with those 300 papers that we had already there, and then we analyze, okay, how do each of these explainable AI papers evaluate their method to eventually get a whole set of methods on how you can evaluate explainable AI. So usually when people talk about evaluation of XCI, it's always the discussion, okay, should we evaluate with users or not? Some say, well, if you want to make sure that it's explainable, then you should definitely evaluate with users. But I would say that there's more to the story than saying that evaluating with users is just the golden standard. So suppose that we train a standard convolutional neural network, but with data which we just has some random labels. Well, we know that neural networks can eventually learn from any data set, so eventually also here the model will give a certain output. But of course this model hasn't learned anything meaningful, so basically we put some garbage in and you get some garbage out. But if we would then apply an explainable AI method to a certain outcome, so E is then the explanation method, and we would show this explanation to a user, then probably the user would say, well, this explanation is weird because I had expected that the model was looking at something else. And then the user might say that the explanation is actually bad. Although it is actually the case that the model was simply bad, but the explanation might actually be really showing what the model has learned. So if we would only evaluate the explanation with users, then basically the evaluation of E and F is evaluated at once, rather than evaluating F and then separately evaluating E. So I would say that if we want to correctly evaluate explanations, we should basically look at two parts. We should evaluate with users to basically check, okay, is the explanation useful and is it making sense? But also, is the explanation indeed showing what the model is doing? And for that, we don't need users. That's actually something that we should check with some other automated methods. And we can nicely illustrate this, for example, with this picture. So this was a paper where they evaluated a lot of explainable AI methods, which generated heat maps. But they also added one extra method, which wasn't taking the model into account at all. It just showed the edges of an image. And you can imagine that if you would show these heat maps to a user and you ask, what do you think is the best explanation method, that people would say that this is actually the best one, because the heat maps look pretty good. But since it's just identifying edges, it could be that it's really plausible to a human, but it's actually not a good explanation method because it doesn't have any link with the model. So we therefore also argue in our paper that if you want to evaluate the plausibility of an explanation to humans, that's really different from evaluating how good the explanation actually is with if you look at what the reasoning is of the model, and that you shouldn't evaluate them both at the same time. So some therefore also argue that actually keeping humans out of the loop for evaluation is actually more fair than using the human evaluation. So there is basically not a single answer on what then makes a good explanation. So what we eventually did is, by reading a lot of papers, that we came up with this list, which are basically 12 different aspects which you can evaluate to say something about the quality of an explanation. And we look at the content, we look at basically how the explanation is then shown to the user, and of course we also have some properties which are about the user. So the coherence that we talked about is basically how plausible, how reasonable is the explanation to the user. This is very important to evaluate, but only one of the aspects that you can evaluate. If we look at the first property, that basically describes how faithful is the explanation with respect to the black box. So the example that I shown before, when you have just simply a model which is showing the edges of an image, then the coherence might be high, but it is not faithful because there is no link to the actual model. But there is of course more which you can evaluate. So for example, suppose that we now have a heat map explanation. Then what you also want is that actually the whole behavior of the model is actually described in the explanation. So if it turns out that this is indeed important for the model, then you should indeed be assuming that the rest is then not important, and it shouldn't be the case that actually there are more important pixels here. And you can also say, well, I also want that if I change a few pixels in the image here, then you do expect that the explanation is actually the same. So similar input should give similar heat maps in this case. And another thing is what people usually argue, well, it's important to have explanations to understand why not this class, or what if this was different. So suppose that this was the importance map of sheep, but now the importance map of cow would have been exactly the same as the one for sheep, then still you didn't have any useful information. So that's also why you then want that explanations are actually different for a different output. So basically, this is a whole list of 12 aspects that we have created, and all of them could actually be evaluated to say something about the quality of an explanation and of an explanation method. And you can then basically see it as that you give a certain score to each of those 12 points, and based on your use case, you can then decide what you think is then basically most important, because it will probably never be possible to focus and to score very high on all of them. So, for example, on the one hand, you do want that everything that the model finds important is in the explanation. On the other hand, regarding on how you are going to show it to the user, the size of the explanation is also important. If you have feature importance, then you might not want to show all the features, but only maybe the 5 most important ones. But it means that if you don't show everything, then so there are a few aspects where you basically choose based on your use case what you think is then most important, and then you can select an explanation method which scores very good on those aspects. So what makes a good explanation is then basically what we have answered with those 12 aspects. But then the question is, okay, how can we then evaluate? So how can we now actually measure how good a certain method is? Well, we did that by looking at those 300 papers that we already had. So from NeurIPS, CFPR, and those other A-star conferences. And we analyzed how they evaluated, and for example, we found that 1 in 3 of these 312 papers, they actually evaluated by just showing some examples, which is evaluating something, namely whether a user finds the explanation good, but of course it's not evaluating some of the other aspects. And then we found that, well, 1 in 5 evaluates really with humans. So they can really ask questions and then give certain numbers about what humans think of the explanation method. And 58% did some other way to put a certain number on the quality of the explanation method. And in our survey, we are actually mostly interested in this one. So, okay, what are then the exact methods that people use to evaluate explainable AI and to say something about the quality of the method? So what we did is that for each of those 12 aspects, we actually collected all the evaluation methods that one has used. So, for example, for the first one, you could, for example, say, okay, we are going to change the internals of the model. For example, if you have a neural network, you are setting weights, you give weights a different value, then you would expect that the explanation also changes. And then, for example, in this case, the showing the edges of an image, then this heat map would still be the same. And that shows that there is no link between the model and the explanation. And then this explanation would actually score really low there. One other method, for example, that you often see is that you start by taking the feature which has the highest importance. So, for example, a certain pixel, and then you are making sure that this pixel is not in the image anymore by making it gray, for example. And by doing that then for all the important pixels, you would expect that then the output of the model changes. Because if you would, for example, remove eventually the whole bird here, then you would expect that the model is not predicting bird anymore. So these are different methods basically to evaluate only one of those 12 aspects. And we have basically collected a lot of evaluation methods, such that basically anyone can really have some tools to evaluate and benchmark both new and other explainable AI methods to really put a number on it. And we have basically done that for each of those 12 aspects. So now I was only focusing on one, but we have basically identified a lot of evaluation methods where no user involvement is needed to evaluate any or multiple of these points, collected from more than 300 papers. And basically, when we were doing this research, we all thought, okay, so the next step would then basically be, rather than only evaluating explainability afterwards, to try to already make sure that we try to include this already when we are training the models. So some of these evaluation metrics could maybe already be included during training, so that we can optimize them already for to make sure that their explainability to users is higher. And that then brings me to the second part about interpretable AI. But let's first see whether there are already some questions about this first part, about evaluating explainable AI.
Okay, thank you. Do we have some question in the chat, or you can raise your hand? Okay, so I have one. So in this paper, you've basically defined 12 properties.
Yeah.
That should be measured on an evaluation method, on an explainable methods, and we have some papers in the state of the art proposing new metrics in order to evaluate these properties. How can we evaluate the quality of the metric itself?
Evaluate the quality of the metric. That's a good question. So it's of course also the question whether there is for each of those 12 aspects exactly one metric. Probably it depends on like if you have an image as input data, that of course might already require a different kind of evaluation method than a different one. To then say what is best enough. So for example, one of the evaluation methods that you often see is I think I had it here in my list as well. Yeah, is that you actually create a method which is by itself already explainable. And then you can, of course, apply your, for example, post-hoc explanation method to this model. And you can then check whether the explanation is actually the same as the true reasoning of the model. So I think if you want to know how good the evaluation metric is, that you should apply it to a model for which you actually know what the true reasoning is. And then you can evaluate whether the explanation actually saying the same as the actual reasoning.
But that would be under the assumption that one method can be transferred to, let's say, another architecture, for instance.
Yes, so indeed, but that's why I say it really depends on the use case to then define what is then, which metric is then the best, and could indeed also be that you just show the numbers for multiple metrics, which is usually also what you see in papers on explainable AI.
Okay, I see someone has raised his hand, so you can ask your question.
Yes, good afternoon, Fateh Kakai from Thales. I would like to ask you if you have evaluated some methods for I would say not only classification or computer vision tasks, but also regression tasks.
Yes, we have. So this survey was really about basically any paper on explainable AI, but we did see that classification was one of the mostly applied tasks. Let's just go back to my overview here. Yeah, so we see that classification, that was basically the main task of most of the papers, but there are indeed also some papers which are on other tasks. And also on the type of data, images was indeed most present in our data set, but we also have papers on text or table data or time series. So on the website that we have launched here, you can basically select what type of explanation, what type of task you are looking for, the type of data, and then you will see that there are still also some papers on other tasks. But I think because of the venues that we have chosen, turned out that classification and imaging was usually one of the topics which was occurring most often in our papers.
Okay, and what is your feeling regarding the maturity of the methods, the tools that are proposed for instance regression tasks and I would say use cases other than classification of images?
So what we in general seen also when we were looking about on the evaluation methods, what we did see is that so we had already here that you see that the number of papers on explainable AI was already increasing for the last years, but we also saw when you look at the numbers on how are people evaluating XAI, that was also really changing throughout the year. So the number of papers which only showed some examples was higher in the first year, and the fraction of papers doing that was actually decreasing in the last year. So you do see that the field is developing itself in that way, in that the evaluation is now done more extensively. How it is exactly then done for different tasks, for that I don't really know. I haven't checked the papers on that, but in general we do see that the whole field is basically indeed developing itself, and that evaluation and measuring the quality is now more important than it was in the first years.
Okay, thank you.
If there are no more questions, I think that we can go on with the next part of your presentation.
Yeah. Let me go through. Yes. So actually go back to one of my first slides. So I said, well, usually what people do is that you have to choose between either a model which is by itself already explainable, but then maybe the accuracy is lower, or you go to a model which is not explainable, but then you apply, secondly, a method to still get insight. But then instead of only evaluating the quality of explanations on those explanation methods, why don't we try to already incorporate explainability already in the model itself? So in this case, rather than applying an explanation method post hoc, why not trying to combine the explainability of an interpretable model, like a tree, with the power of a neural network? And that's basically what I did in the other work that I'm now going to present, which is basically a tree, but it's also neural. So we are basically merging the power of neural networks with the explainability of trees for interpretable fine-grained image classification. And this was presented as CFPR last year. So let's say that you have an image of a bird, you can forward it through a neural network, and then the model can say what type of bird is actually in the image. If you then would, for example, have post hoc explainability, and you want to know, okay, why is the model giving this output, then you can, for example, apply a heat map. And this is giving the users some insight into what the reasoning was, so you can know which areas were important. but still it doesn't give the user enough information to fully understand the reasoning. It's basically nothing more than just the first level of explainability about feature importance. So instead, what if we could make the model in such a way that the reasoning is actually following steps similar as in a tree, such that the model is by itself already interpretable. So rather than later applying an explanation method, we are basically saying that, okay, the classification is already done by this model. So E and F are basically both the same. They are one model. So how this then looks like is actually the following. So this is our tree. And each node contains a certain part. And basically what the model is doing is that it's going to look whether such a part is then present in a new input image. And the prototypical parts are taken from the training data. And the reasoning is basically that you start at the top node and the model is going to look whether this prototypical part is present in an input image. If yes, then the model goes right. If not, then the model is going left. So for example, if you have an image of a painting bouncing, the model will look, okay, is this prototypical part present? Yes. Is this prototypical part present? Well, no, because it's looking for some black wing, which is not there. Is the head blue? Yes. Okay, and that's why the model then is presenting that this should then be the type of bird. So the whole reasoning is on a global level is now understandable to a user. Basically, the whole model is available. But the power of neural networks is used to identify the presence or on whether such a prototypical part is actually present in an input image. In case that the user is not interested in the global logic, you can also show the local explanation. So only show the reasoning for one single sample. So in that case, suppose that you have a test image, you can just forward it through the tree and you show the certain path in the tree. So you first check, well, this prototype was found here, this prototype was found there, the third prototype was not found, and that's why then the model is predicting this as label. So how does it work then, the training of these trees? So we have a convolutional neural network. This can be basically any standard convolutional neural network. You give an image X as input, and what a neural network then always does is that it outputs a set of feature maps with height H, and we say that feature maps are square, so the width is basically W, but that's usually equal, and then a number of feature maps D. And generally, it's the case that if a CNN is looking at a certain part here, then that corresponds to the same location in the latent space, so in the feature maps. So this value, this patch of the latent space will roughly correspond with the patch here in this input image. And that is something that we can actually use in our tree. So basically, usually when you have CNN, you have these feature maps, and then you're just adding one extra layer, which then predicting the classes. Instead, we don't have such a standard fully connected layer, but we have a tree architecture as last layer. And each node in the tree consists of a latent vector, which has the same size as one patch here. So 1 by 1 by D. And this latent vector is actually the prototype that we eventually are going to use in our model. So how it works is that, well, the model gives this latent embedding of the image, and this consists of patches. And the model is going to calculate the distance between one patch here and the values here of the prototype. So you get this distance, and then you can get a score between 0 and 1 by taking the x of the minus distance. And you can calculate that for all the patches to then select the nearest patch. So in this case, this part of the image corresponds most to this prototype. And then by calculating the distance, you get a certain similarity score. So how present is this prototype in the image? Now a standard decision tree then goes either left or right. But in our case, we have a so-called soft tree, which means that we route the sample to both branches, but with a certain weight. So in this case, suppose that the similarity between this prototype and this patch was 0.8, then we say, okay, for 0.8, the sample is going right, and for 0.2, the sample is going left. And then you can calculate again the similarity between this prototype and any of the patches in the set of feature maps to then again get a score. And at the same time, so the model is learning these prototypes, and at the same time it's also learning the leaves. So which class should actually be present in any of the leaves. And the final prediction is then simply the weighted average of all of the leaves. So 0.2 times 0.4 times the class distribution learned in the first leaf, plus 0.2 times 0.6 times the class distribution in the second leaf, etc. And this is then giving one, eventually, again, one distribution over classes, which is then the prediction, and then you can just use the standard loss by using the label to then optimize the model. And then the class distributions will be optimized, and also the values of the prototypes will then be optimized. So eventually the model will learn, okay, what are the best values here in order to get a certain routing such that we get a good classification accuracy. But until now, the prototypes are, of course, still some latent vectors of length d. So how can we then eventually give meaning to them? Well, we visualize them eventually as patches of the training data. And we do this basically by, once the model is fully trained, we again forward the whole training data set through the neural network, and we look for the nearest patch to this trained prototype. And that's eventually then the patch that we are going to use. So if this will be the nearest patch, then we take the same part here in the input image, and that's eventually the visualization of the prototype that we are going to show to the user. And we found that actually usually the distance is 0.0000 something. So we could basically really map one prototype to a certain image patch. So this was developed for fine-grained image classification. And that's why we evaluated on the birds data set, which has 200 different types of birds, and also on the cars data set, which has 196 classes. And what is important to emphasize is that we really only use the class label, so we don't have any other information about parts present. It's really, we only have an image and a label about which object is in the image. And which parts the model should look at is then actually learned by the model itself. So we have fine-grained image data set with only class labels. We don't require any other data annotations. And the model has to learn the prototypical parts in the nodes, and it has to learn the classes. And we find actually then that the accuracy is quite close to a standard neural network. And with, in our case, the advantage that we have both local and global explanations, which are, because with design, really truly showing the reasoning of the model, because the tree is actually the reasoning of the model rather than having a separate explanation method. So what are then the results? Well, there was already one other model which are also using prototypical parts, and what they do is that they have a fixed number of prototypes per class. So in case of the birds data set, we have 200 classes. They have per class something like 10 prototypes, so you have 2,000 prototypes in total. And then they are eventually giving points, and then the final predicted class is the class with the most points. In our case, the reasoning is actually way easier, and you can also see that in the number of prototypes. So whereas the existing model ProtoPNet then has 2,000 prototypes, our tree only has 202. So a bit more than one prototype for each class on average. If you don't want to get access to the whole model, but actually just want the outcome explanation of a single image, you can only look at one path in a tree. And then you even get down to a bit more than 8 prototypes per output, rather than still having this 2,000 prototypes to look at in the other model. And in terms of accuracy, you can see that we are actually still scoring high. But most importantly is that now we have a certain size, which is for user actually also understandable. We also quickly looked at, okay, how does this then compare to other neural networks? Well, the best neural networks that we could find for an image size of 224 by 224 was actually 87 and 93. And then we see, well, with one protein, we are not really there yet, but we can also use multiple proto-trees. We didn't do anything smarter. We just trained the same tree multiple times and then took the mean of the outputs. And then you can see, well, the number of prototypes is still lower than one model which was already out there. And still the number of prototypes is something which is relatively small and easy for a human to grasp. And then you see that accuracy is really close to a model which is not explainable at all. So when people talk about, like, is there a trade-off between the performance and the explainability of a model? So should we choose between a simple tree with bad performance or a big neural network, but then it doesn't have any explainability? We actually argue that we don't think it's the case, and that we can actually merge forces and have the power of neural networks with the explainability of some models which are interpretable. So, but rather than using the neural networks only for classification, let's use them to learn features which are interpretable for users. So some kind of automated feature engineering, like in the past humans did feature engineering. What about using neural networks to do this feature engineering? And then we can use these features, such as we have done in our case, that you have these parts. You can use those then in a model for explainability. So use prototypes in a tree, and then you basically have, still have the power of neural networks, but also the explainability to a user. And then to evaluate basically how good those interpretable features are, we could then use the insights of those properties that I presented in the beginning of the presentation, that you can basically evaluate based on the evaluation method that we found how good those interpretable features actually are, both on the performance on the task you're interested in and also on how interpretable they are. And then basically a research question for anyone working in a certain domain is, okay, what are, for your use case and for your users and for your type of data, what would be interpretable features? And how can machine learning learn them? So until now, I really focused on image data, and then we said, well, an interpretable feature could be a certain part. So we a patch of an image. If you think of text data or time series data, we should now think of, okay, how can we maybe try to create interpretable features for those kind of data types? And then I think that we can really use the power of neural network for getting a high performance, but still also really getting useful insights from all the computer science research which is done in the past about the more simple interpretable models, and actually merge forces to eventually get explainable models which are well performing. Yeah, and I think that our model is now one of already a really nice example of that and how we can merge forces. So that was my talk so far about evaluating explainable AI and interpretable image classification. So are there any more questions?
Thank you very much. I see that we have at least 2 questions in the chat. The first one from Luc Etienne. I may have missed the information, but I didn't really get how you choose the prototypes and the number of them in the tree. Are they the result of the training phase, or does the training only determine the weights of the edge in the tree?
Okay, yeah, good question. So no, the prototypes are really learned by the model itself. So the only thing that the user has to define is if you have a certain height of the tree, and then basically the architecture of the tree is fixed. So if you know that you have 200 classes, then you know that you need at least a certain height to make sure that the number of leaves you have in the tree is enough that each class correspond to at least a certain leaf. So the architecture is then fixed, and then the model will then learn the values for these nodes. So the model itself will then learn what are actually good parts to focus on in order to get a good classification outcome. So what you then, for example, also see is that, for example, all the birds which, I'll go back to the image here. So for example, here you see that these birds are all having some same parts, namely that part of them is red. And the model has then actually learned that, okay, it's really useful to focus on this part. So then basically all same birds are already clustered in one subtree. And then the model will learn, okay, and now it's maybe best to use this part. So the prototypical parts are really learned by the model itself. Yeah, so the only thing the user has to define is to what is the height of the tree. So how many prototypes are there to learn. Similar, if you have a standard linear layer, you also have to define the number of nodes beforehand, and then the rest is learned by the neural network.
Okay, we have another question from Clovis. Decision trees are known to be prone to overfitting, since as one goes down in the classification tree, the data grounding the decision becomes very little. What trick have you used, or why your tree methods does not overfit?
That's an interesting question. So what we actually found is then usually overfitting happens when, for example, only one of a few samples are ending up in a certain leaf. But what we actually found is that usually, since we have a bit over, for example, with this birth data set, we had 200 classes and 202 prototypes. So there's a bit more than one leaf per class. And then you see that there are actually enough samples which are ending up in a certain leaf. So we actually didn't notice any overfitting. Also because the user has to define beforehand what the number of nodes are. So if you would set the height very high, then maybe the model will overfit. But again, the power of neural networks is usually already that overfitting is not necessarily happening if you are training a CNN with all the standard tricks that we currently have. And that's basically what we are doing as well. So you would expect that then the latent embedding that you basically get as input here, that is all actually being able to make sure that the model isn't overfitting too much. And then that's then the input that you're then giving, yeah. For the tree. So I think that will already help with making sure that the model is not overfitting too much.
Okay, I see that there are all the questions in the chat. I'm just going to jump in because I think that my question is related. You said that the decision at the end is a soft decision because it's a weighted sum of all the leaves.
Yeah.
So as a user, I might understand a hard decision path, but how do I understand the fact that this is, I don't know, an indigo bunting, or I don't know the species of the birds, but
Yeah.
because it's a 0.5 this species, and this okay, not this species particularly, but it's a 0.5 that particular branch in the tree plus 0.01 that particular branch in the tree, and so on.
Yeah, indeed. So we could also imagine that having this soft routing is maybe for a user difficult to understand. It's just we needed it for training the neural networks to make sure that the gradients are actually flowing from all from the leaves through the whole model, rather than only optimizing one certain branch through the model. But what we also have, since we have just a standard loss term, is that the model always wants to give basically a really high confidence that it's a certain value. And by using the standard loss term, because you want to optimize the model to be very confident on one class, the model actually itself learns already to give very high similarity to one side and therefore have very low values to the other side. So what we also show in the paper is that you can actually then, after training, you can change the soft routing to the hard routing, and basically the explanation state, the prediction stay almost exactly the same. So the model had itself actually already moves from soft routing to hard routing. So then it's 0.95 this to the right and 0.05 to the left. And then eventually in practice, we can just convert the soft reasoning to the hard reasoning. So it's actually only soft during training, and then during testing it's actually hard. And then it's indeed very easy for a human to understand. And you can really show one single path in the tree rather than the whole soft reasoning.
Okay. So I think that there are another question related also to the depth of the tree. Luc says, okay, thanks. I get you kind of use brute force to determine the height of the tree, or at least some kind of binary search. And Julien said, how do you handle the depth of the tree? Is it something that is learned through the data or hyperparameter?
Yeah, so it's not learned, but it's basically like suppose that you have a data set with 100 classes, then it wouldn't make sense to create a tree with only a height of 2, because then you have just 3 nodes, you have 4 leaves, then you can of course never classify 200 different classes. So basically you need to define the height so that you have at least the number of leaves as you have the number of classes. And what we then show in the paper is that if you have that number, then it doesn't matter if you increase the number more, then accuracy is almost the same. But if you get lower, so you have fewer leaves than the number of classes, then accuracy is of course low, because it simply hasn't, it's not possible to really classify with high confidence one class if you have to put multiple classes into a single leaf. So basically just calculate like, okay, what is the height that I at least need for my number of classes? And usually, at least for our data set, that then works.
But what happens if you put a huge amount of, a huge depth?
Yeah, so that's something that we haven't tried. So we went up to, for the bird data set, you need, I think, at least a height of 8. And we tried until 11 or something. And that then still worked fine. But indeed, I don't know what happens if you set it too big, but then of course the model also gets bigger. So then the model training is also getting very, very slow. So I don't see any reason why you would set it so much higher than the number of classes you have.
Okay, we have 2 questions from Fateh. The first one, do you think that this hybrid approach can scale for use cases like object detection on aerial images or semantic segmentation with a lot of objects and different classes to be detected?
Yes, so I think in general, yes. So I don't think that our model here is then now already useful to apply on all these different use cases, of course. But I think the general idea, which I presented also here in the last slide, I think that is actually useful. So that we say, okay, you want to use neural networks for learning interpretable features, and then we can learn those features into a model which is for user explainable. I think that underlying idea is something that can be applied to many different use cases, but for aerial images, for example, prototypical parts might not be the best interpretable features. So you can then think, okay, what will be other features in this domain which are useful for a user, and how can we then create machine learning models to actually learn them? So I think these are the interesting research questions for these kind of use cases for the coming years.
Another question from Fateh. Have you applied the evaluation criteria that you presented in the first part of the talk, of your excellent talk, sorry, to your hybrid explainability method?
Yeah, that's an interesting question. So the survey that I did was after the model that I had developed. So no, I haven't applied all these evaluation methods yet, but it's something that I'm currently working on, and I'm therefore also working on a new improved version, which will probably score higher on the evaluation methods than the model that I have here. So we see basically that the whole field is developing, and whenever there are basically new insights, and what I noticed that because we now have this list of evaluation methods, you can very clearly see, okay, what is actually now the aspects where the model is already performing well, and what are the aspects which is maybe scoring lower. So it actually really helps you to give some clear starting points on where we can actually now do more research and where we should improve the model.
Okay. Do we have another question?
I have a question, if it is possible.
Yeah.
Okay, thank you very much, Mikey, for your talk. So I have a question about the notion of interpretability. So you say that the prototypes that you provide are interpretable. For me, they are visual. But you see, for me, interpretability comes with some form of semantics. And you see in the example that for some of the prototypes, it is difficult to give them a semantic. Some others, you can say, okay, it is a beak of the bird, but some others, it is just a part of the image. So I'm a little bit frustrated about this notion of interpretability. So
Yeah.
can you have you some try to do to find to relate some semantics or how to do it? Do you have some idea about that?
Yes, yeah, definitely. So what I mentioned is that indeed, if we use neural network to use interpretable features, then we should also evaluate not only the performance, but also need how interpretable those features actually are. And for example, what I'm now developing is that we evaluate the interpretability of the prototypical parts by looking at the labeled parts in the dataset. So for example, the birds dataset does have labels of this is the beak, this is the tail, etc. And then we try to map, okay, if one prototype is always found in a certain part of the image, is that then indeed always the beak, for example? And if that's the case, then you indeed are more certain that indeed this prototype has a certain meaning to humans. If it would not be the case, it could still be that it has a meaning. It could be that, for example, always looking for something blue, so then it's not correlated to a certain object part, but it's still correlated to a human concept. But trying to make metrics that can evaluate that's indeed something that we are now working on. But it is indeed the case that sometimes it might be difficult to give meaning to a prototypical part. We saw it especially at the top of the tree. So then you have one node which is basically splitting the data set into two halves. Those prototypes at the first layers of the tree are usually indeed harder to grasp. Okay, what is the exact meaning of this prototypical part than the parts at the last layers, because then usually they are actually more interpretable.
It's interesting because usually at the root, it is more discriminative. So it is strange that the most discriminative prototypes are less interpretable. So it is
yeah, well, it's mostly because you then want to find a prototypical part which is basically present in roughly half of the data set, so that you can split it. But what object part is present in so many different bird species? So, for example, also what we sometimes saw is actually that the model wasn't looking at a bird object part, but at something else. For example, it was looking at leaves in a tree, because there are some birds always at the sea and there were some birds in the forest. So to basically split those two groups of birds, it just looked at whether there were leaves visible in the image, and that was then a prototype. And that is interpretable to humans. It's of course the question whether you want a model which is basing these decisions on those background prototypes. But again, that's why explainable AI is so interesting, because then you now actually get insight into the reasoning of the model, and that the model has apparently learned to make a group of water birds versus birds in the forest.
Okay, thank you.
Yeah, you're welcome.
George?
Yeah, okay. Thanks for the talk. That was very interesting. I have a question similar and related to that of Marie-Christine, actually. Did you try to probably you did look at the prototype and try to figure out which part of the image they caught, and how is it possible to somehow cluster them or match them with specific parts of the bird?
Yeah, so we are basically now looking into it indeed to see. Basically, if I understand it correctly, there are two questions. One is that whether we can link if you have a prototypical part to a part in the image, and that is basically yes. So we can basically the model will output. Let's go to this slide. The model will output. Okay, I have found this prototype here in this part of the image. So that's already explained by the model. If you want, for example, to have a different prototype in the image, that's also something that we are now working on. Like how can a user maybe change the prototype? So if you have that the model is focusing on leaves to distinguish between two groups of birds, then you don't want that the model is using that background information. So we are now so indeed thinking about ways. Okay, how can a user maybe change the prototype to something that the user is actually interested in. Does that answer your question?
Yes. Do you think you can force, by adding something, the prototypes to be aligned on some parts of the bird, either directly or automatically with methods like probably you know how Roma is doing this.
Yeah, so it's the goal of this model was really that we didn't want to use any more data annotations than just the label of the image. So we haven't implemented it. But yes, I do think that if you have a data set which has, for example, labels of object parts, then it would definitely probably be very useful to give that as extra input when the model is training. So rather than, indeed, as I said before, only evaluating for explainability afterwards, let's indeed use the method that we use to evaluate already, try to incorporate it during training. And I do expect indeed that then the prototype quality will actually get even better, but it's not something that we tried. We really want to make sure that it's also applicable to data sets which don't have these extra part annotations in there.
Actually, Roma has a method for doing that without local annotations. It is quite coarse, but it's stabilized on a specific part. Also, so far, your method is your explanation is only visual. Do you think you can make it more symbolic? For instance, typically, if you say this part is a chest, this part is a beak, this part is a wing, and this prototype has it red, this prototype has it multicolor or whatever.
Yes, so one other paper that I have actually goes further and says, okay, now we have this certain part, but what is now exactly the meaning of this node? Because currently it's just an image patch, and there we then try to give the user even more information about what the meaning of such a node is, by saying, for example, well, what is now most important here? Is it shape, for example, or for here in the wing, is it because it's because you see these small stripes of the wing, or is it more just because you have on the top something black and on the bottom there's something red, for example? So whether color is important or shape or texture. I also have a method which actually then evaluates that to then basically explain what is now most important. So what is this explanation really showing? So in that sense, when you go further than only showing the image patch. And I do indeed think that if you, for example, have data annotations, and you can indeed measure, well, actually this prototype is always activated on the beak, then you could indeed also add a textual explanation to the user that it's really about the beak. So I do indeed think that there are other steps possible to explain the prototype even further. Yes.
Okay, thank you. I have another question on the first part of your talk. Our team, we also work on a video, and you mentioned very few, about 2% of the papers related to video. So this is basically around 6. So maybe.
Yeah.
So what are they about, this paper? Do you remember? Because this is 2% over 300 papers.
So your question is about
the 2% in video. Only 2% of the papers. So typically about 6, we are dealing with the video data. So
yes.
In our case, we do try to explain how a visual content of a video matches a textual query. So are these papers about this type of subject? And what do they say regarding explainability?
So I don't know off the top of my hand what these papers are exactly about, because we have read more than 300 papers. Yes. But we have included it here on our website. So if you then select for the type of data, the video, then you would see all the papers which we have labeled as they are using the video data, and then you can basically check yourself. What those papers, what the topic of that paper then really is.
Okay, we'll have a look. Yes.
Yeah.
Thank you.
But there are probably, of course, more papers on video and XCI. It's just that the conferences that we have chosen, I don't have the list anymore here. Here, yeah, that probably there are not so many papers on video. But if you might know other conferences which do have more.
Yeah, actually,
video.
I don't see SEM multimedia, for instance.
No, exactly. For example, yeah. Of course, we also had to make a choice on which papers to include and which not. So our website is just a starting point, but definitely there are even more papers out there.
Okay, thank you.
Okay. if there are no more questions, I think that we can thank you again for this very, very interesting talk.
Thank you.
You're welcome. And yeah, again, if you have any more questions, then you can always just if you send me an email, then I'm happy to answer you, and maybe have another talk about a certain topic.
Okay, great. I'll probably send you an email later on in the day to so that we can set up a meeting to discuss this.
Yeah, sure.
But thank you again. This was very, really interesting. There were a lot of people.
Yeah.
Yeah.
Yes. Thank you very much.
You're welcome.
We can stop the streaming.